So this morning we're going to kind of cover this light subject called primary secondary pumping. It's a subject that I've been involved with for quite a few years with my time at FIA. It's been around a long time, so we're going to talk just a little bit about where it came from, and probably as important or more important, some of the details, how to use it. If you're in the design engineering world, how to apply it or make sure it's applied properly based on your design drawings. If you're a contractor and you're installing equipment and the equipment manufacturers are recommending using this technique, just be comfortable with why. First of all, what it is, how you do it, and why are you doing it. Radiant heating, another big application for primary, secondary. Chilled water plants, multiple boiler plants. So there's a lot of different reasons or different applications that primary, secondary, it's not that it has become popular, but there are a lot of popular applications currently. It was around, developed a long time ago, didn't see perhaps as much use. And then with some of the advent of different technologies with regards to cooling and heating of buildings and homes, it's kind of found a rebirth, if you will. So it's an interesting subject. You can get a little confusing at first, but to some of you, this might be just a general review, and we appreciate that. So like I said, if you have a question, reach down to the chat, just type it in, Rob will grab it, and we'll go from there. So what is it? What is primary, secondary? You can, I'm just going to go through a couple quick examples here, but you could go through almost every boiler manufacturer, current manufacturer today, and go through their installation manual. And you'll see drawings, something similar to that. Well, you'll see.
Well, where do I turn it on, Mary?
There we go. So anyways, you'll get into any one of the current boiler manufacturers' installation manuals, and you'll see some type of picture to this extent. And you might even kind of explode it, and you'll always see this expression, or pretty close to this, you'll see this expression, not to exceed 4 pipe diameters, or a maximum of 12 inches apart. You go to another manufacturer's literature, you'll see the same thing. Here's that maximum 12 inches apart. Why are they highlighting that? What's going on? Here's an example when you get involved in the radiant heating installation practices. And with radiant heat, a lot of times you're looking for maybe lower water temperature than, say, the rest of the heating system, fan coils, baseboard, etc. are going to want to operate at. So you'll mix it down. And here's a quick example of a variable speed injection pumping. The thing that I'm just trying to highlight here is look at note 1. There must be a maximum of 4 pipe diameters between the T's. You show a picture here of another author in the industry is talking about a 4-way valve with a boiler loop and then some radiant tubing over here. And the way he's interconnecting the radiant loop over here to the boiler loop is with some closely spaced T's, that magic distance. One last picture here, and again, talking radiant heat, instead of doing an injection pump, they're showing a mixing valve going over to perhaps a radiant loop from the higher temperature boiler loop. And if you look at note 1, there can be no more than 4 pipe diameters between the T's in the boiler loop when you're connecting the radiant loop. So the question is, well, why? Why 4 pipe diameters? What's the magic behind that? Or what's the technical reason behind that? So I guess to get into that, what I'd like to drag in is just a little bit of history as to where it came from. And then as we go through that, it'll become clear why the 4 pipe diameters, or why the maximum of 12 inches, etc. And sometimes that's not even actually accurate, but we'll discuss that as we go. So a heating engineer, kind of a famous heating engineer that worked at Bell & Gossett for a long period of time, Gil Carlson was his name. In the engineering community over the years across the country, they considered him the father of modern hydronics. And he invented a few different items that I'm listing out here, and specifically what we're talking about this morning is he was the person who developed this concept of primary secondary pumping. And you'd say, okay, well, why and how? Why did he do it? And like everything else in life, sometimes necessity becomes the mother of invention. And so there was a large monoflow heating system. We don't have to go into great detail, but there was a large monoflow heating system with huge problems, big problems down in New York City quite a few years ago. And it consisted of 10 garden-style apartment complexes being fed off of a central plant. And when they went to commission the system, they couldn't get heat out of any of the radiation in all 10 buildings, which definitely classifies as a problem job. And back then in the time, there were no manufacturer reps. There was just manufacturers, and then you'd have factory offices scattered throughout the country. So there was a factory office out in New York City. And so they were involved with the design of it. So they went out to look for some help, try to help the people, the installing contractors. And they were scratching their heads. They couldn't figure it out. So they reached back to the factory. And so the factory at the time had a young engineer right out of Purdue University named Gil Carlson. So they suggested he hop on a plane and fly out to New York City and see if he can come up with some ideas to get them out of this problem that they're experiencing. So just a real quick overview. This is what was going on. It was just an unfortunate situation where we had a large system being designed, and they were using two separate engineering firms. And one firm made a mistake, who was responsible for designing all of the inside piping and terminal units within each of the 10 garden-style apartment buildings. And the problem that they made unknowingly is they oversized the piping inside the building. The second engineering firm was responsible for the central plant, and then just the main that fed the whole system, fed all 10 buildings. And unfortunately, their mistake, which they didn't realize, is they undersized the main piping. And dealing with the monoflow system, that's resulted in a big no-no. And what I mean by that is when this piping here is too big inside the building, and it's a monoflow system, and this piping here is too small, so I don't have adequate flow rate, it led to a serious problem. Real quickly, stepping back in time, monoflow systems. And the way they would work is you would have velocity along this main here. And as that flow rate, that certain velocity is moving through the piping, all of a sudden it encounters the cone. And that's basically an engineered pressure drop is what a monoflow fitting is. So this pressure drop here caused, because of this higher flow rate velocity through the main, would encourage a certain amount of water to move off of that main and divert up through the terminal unit, through the radiation, and then back down. And that's how a monoflow system works. And in this particular job, the piping inside each individual building was too big, and the piping along the distribution side was too small, so they had inadequate flow. So Carlson goes out there and he establishes this. And he kind of does some calculations, and he determines that the main is providing about half of what was designed, what was needed. And then he realizes that the terminal units are already installed, that everything's been designed, and the radiation was looking for an average water temperature around 200 degrees. Based on a 20 degree delta T, you'd have a return temp of about 180 coming back from each building. So that's what was designed. And then the problem was the system could only provide about half of the design flow rate. And this is what he's wrestling with. And he comes up with an idea. And he tells the contractors to put in booster pumps inside each building based on the load of just the building's load. And the factory people from Bell and Gossa that were out there in New York, they're like, Gil, you can't do that. You can't put little booster pumps in series with a large distribution pump. You got a 75 horsepower pump here. This pressure differential would just rip apart the coupling assemblies and overload the motors. You know that you can't do that. That's very bad design practice. You're not supposed to do stuff like that. But here was the hitch. But then he said, install a piece of pipe between the supply and the return of each building's individual supply and return. And he referred to it, he called it back then, a common pipe. And he said he wanted to hydraulically isolate the distribution pumps from the individual building booster pumps. And I'm sitting here, we're talking, it's 2020, I'm clicking away on a mouse, showing a PowerPoint. Up to that day, no one in the hydronics world ever did that or even thought about it. Didn't even know, didn't see that that was an option. And he did, and he had him do it. And the funny thing is someone out of Bell and Gossett years ago had the brains to put him in the Little Red Schoolhouse in an education room all by himself with a video. And someone videotaped all of his theories and discoveries and what have you. So I was fortunate enough to come across these videos. They were all cassettes at that time. We got them converted. But anyways, so I just took a couple of screenshots. So everything I just described, I'm not making it up. I just listened to him present it to the industry, or actually to the Little Red Schoolhouse where they recorded it. And he talked about what he saw and why he told them to do what he did. And so just as a quick example, what we're showing right here is, he said, one of the buildings, the design load was 400,000 BTUs. And when you're doing your calculations and it's based on a design water temperature of 200 degrees with a 20-degree delta T, you can establish a flow rate of, let's see here, 200-degree supply, 180-degree return. I'm going to have a flow rate of 40 gallons a minute on this booster pump right here. 40 GPM, 20-degree delta T is equivalent to 400,000 BTUs of energy. So he's figuring out on this one building, saying this is how it's going to work. This is what we need to do. He determined that what was coming off of that main, like we said earlier, was only half of the design flow rate, which in this case would be about 20 gallons a minute. And he knew that the return coming back from the building is supposed to be at 180 degrees. The final thing that he had to figure out was, how do I take 20 gallons a minute here and provide a building that needs 400,000 BTUs, that is designed to see 200-degree supply and 180-degree return. So he was trying to calculate what temperature is required from the boiler coming out of the central distribution plant. And so, I'm not sure if you guys have seen this. I think a lot of you might have. We actually did a class last week on the system size, just how useful a tool it is. So I'm just taking this to use it as an example. When I use scale 1, a lot of times I'm looking for GPM. In this quick example, he's saying, I know the GPM. I want to move, in this case here, this white band is listing the BTUs per hour in thousands. So when I find 400, I'm looking at 400,000 BTUs, and I'm just reading straight up. And what I'm looking at is the necessary delta T to deliver 400 MBH with a flow rate of 20. So what does he do? He has the contractors go back to the mechanical room, probably like a Cleaver Brooks boiler or something to that effect, a big old steel fire tube, and it has him raise the aquostat. And he raises the aquostat to 220. And so now what's happening here is I have 20 gallons a minute of 220 entering this way, and I have 20 gallons a minute of 180 going back to the central distribution plant. So there's my 40-degree delta T across this 20 gallon a minute loop that can provide the required 40 gallons a minute of 400,000 BTUs. And so what he could see, and we're going to talk about this, is he could see he could take some of this return water, blend it with some of this extra hot water to get the design 200 degrees. That's the thing that he could see in his mind that no one else had seen. Just real quick, again, one more snapshot just of him explaining it, explaining the math that we're going to talk a little bit about this morning. And the thing that I get a kick out of, and the only reason I have this picture here, is B&G every year would provide an engineering manual to the industry, to the engineering office, to the wholesale distribution, everybody that was involved with hydronics. And the reason I have this one here highlighted is in 1954, this is the first time that they have this expression of this phrase, primary and secondary pumps. And they show a quick drawing. If I back up a quick second, when he goes back to the factory after having this problem resolved, he doesn't say anything to anybody. And the people that worked at the factory, worked for the factory in New York City, get on the phone and they call the lead engineers. And they're like, you can't believe this. The building's working perfectly fine. Everything's heating. It's just amazing. The guy really come up with a real interesting solution. So the engineers, after the phone call, called Gil into their office. I said, Gil, what'd you do? How'd you solve it? He said, I had the contractors put in smaller booster pumps that were capable of supporting the individual building loads. To which the engineers all exploded. Well, you can't do that. The larger pumps will damage the smaller pumps. And he said, well, I had them put a common pipe. I had them hydraulically isolate the loops, one from the other. And they're like, what are you talking about? So he sat down and explained it to the lead engineers at Bell and Gossett. So this was the first year that they actually started talking about it. And then from there, it's moved on to that we use it every day in boiler manufacturers, radiant manufacturers, tubing manufacturers. I just find it interesting. So once they understood the concept, they basically kind of set him free. And they said, okay, go out to the industry and start talking about this concept, to which he did. And Gil is a very, very smart person, very genius-like, very difficult to watch and listen to because very wordy. But what he said here is when two piping circuits are interconnected, flow in one will cause flow in the other to a degree depending upon the pressure drop in the piping common to both. You say, what? That's a lot of words right there. He's describing a monoflow system. Flow in one piping circuit will cause flow in another based on the pressure drop that's common to both circuits. This is how a monoflow system was designed. That's how it's supposed to work. Flow in one will cause flow in the other based on a pressure drop. So then he says, let's flip that sentence around. When two circuits are interconnected, flow in one will not cause flow in the other if the pressure drop in the piping common to both is eliminated. And this is what he meant. Here's my main piping, we'll call it the primary. I take my standard T and my monoflow T. I get rid of the monoflow. I back both standard T's. I get them close together. He referred to it as common pipe. Flow in one will not cause flow in the other circuit if the pressure drop in the common pipe has been eliminated. There's no encouragement, there's no pressure differential, not enough of a pressure differential for the water around here to flow through that secondary circuit. He eliminated it. Then he says, add a secondary circuit pump. And the sizing of that pump is to provide the design flow rate through the secondary circuit. And all you care about is whatever the corresponding secondary circuit's pressure drop will be. Whatever size pipe, what's the flow rate, radiation, terminal unit, whether it's a heat exchanger, makeup air coil, a boiler, a chiller, whatever it is, that secondary circuit pump is sized just for that one item and whatever that corresponding flow rate and pressure drop is. It looks something like this. All that pump cares about is the desired flow rate at and overcoming, based on frictional resistance, the head loss of that one circuit. That's all the secondary pump's job is. Another comment that he would talk to the community, the hydronics community about was, where do you put that secondary circuit? Does it matter the location? And it did. And what he would say to them is, when you'd reference the common pipe, you want to make sure that the secondary circuit pump is pumping away from the common and into the secondary circuit. He was very adamant about that. And the reason is, if you were to put that secondary circuit pump on the return pumping at the common pipe, you'd have some static pressure issues where the system pressure would drop on the suction side of the pump. They actually used to highlight this in one of the training manuals. Real quickly, all we're trying to show here is, here's my primary pump. Solid line is system fill pressure. Dashed line is the pressure differential of the pump. And it increases when the pump turns on because of the location of this expansion tank, which is actually another class we have coming up later this week. As that differential is starting to decline because of frictional resistance, the secondary circuit pump references that pressure there and makes a decision and adds it to the secondary circuit's pressure. If you were to locate it on the return here, pumping at the common, all of this would show up over here as a drop in pressure. And you could create all kinds of air problems about that. So there wasn't a comment. And here's just a quick everyday example that we probably don't spend a lot of time thinking about. But when I connect, and in this case here today, a modulating condensing boiler from the primary loop, we'll call it, and I'm calling it the primary because here's my distribution pump, here's my air separation, here's my expansion tank. I'm pumping out into the building. As I'm coming back on the return, here are my two T's, closely spaced. Here's my secondary circuit pump, pumping away from the common pipe, positively pressurizing the loop, the heat exchanger, I should say, through the secondary circuit, which just happens to be a ModCon boiler. That's a perfect example of that. And that is correct. For a while there, back in the early 60s, they actually came up with a fitting. They tried to change the industry from doing zone pumping with zone valves to do primary, secondary, and maybe sell more, a little smaller booster pumps. So they come up with this dual flow control valve for primary, secondary zone control. And all they were trying to show here is if you were going to do primary, secondary with a small booster pump, these are all the various items that would make up that connection. And they say, hey, let's put it all into this one fitting. And the only other thing you needed here was the booster pump itself. They had some, this is a quick example. I had only found one, I had an apartment building out in Worcester, Massachusetts that had 24 of them. And one of them had developed a leak. And so it now sits at our education room in FIA in Woburn. And to solve the problem, the guys ended up doing kind of what you would have done without those fittings. They just piped in a couple of closely spaced T's, shut-off valves, flow control valves, and they got the system back in business. And I got one of those fittings to sit in our education room. They did some engineering drawings, one pipe primary. They talked about two pipe. We don't have time to get into all those different details, but they tried their best. And within a very short period of time, they stopped manufacturing the valve because it just didn't catch on. The industry wasn't ready for it. Fast forward, 60 years or more. Here's just a quick example of a modern day. We represent a manufacturer called Webstone, and they make a primary secondary ball valve, which is very convenient for purging that smaller secondary loop, whatever it consists of, a boiler or a fan coil or what have you. So we do primary secondary quite a bit today, but back then it just didn't catch. The industry wasn't ready. So just a couple of details that he would emphasize when you're either an engineer and you're designing, you're a contractor and you're installing, you're a technician and you're out in the field trying to troubleshoot a job that doesn't seem to be doing what you want it to do. Be aware of just a couple of little details that will make or break a successful primary secondary application. So the common pipe, he referred to that. And initially when he wrote the manual, the common piping is designed for a minimum pressure drop and can vary in length between a short nipple and 2 feet. Rule of thumb, here we go. 3 to 4 pipe diameters, you'll see it all across the industry. Center line to center line on those T's. I found him in a video where he actually makes this one reference. It's the only time we've seen it. We haven't been able to find it yet in writing. Maximum pressure drop should not exceed 2% of the secondary pump's head. It was the only time he mentioned it was in one of the videos that we have. And he's talking about it here. So you have to have, for a true primary secondary system, you need a common pipe. We had a drawing come in from a contractor that was following a drawing from an engineering firm, and there was debate over whether this was primary secondary because it didn't quite look like it was. So we had to break it down. And literally, if you just kind of did a hand sketch, what we have is we have the boiler loop, 4 boilers with their own pumps, flow control valves injecting into this loop here. We have a distribution pump that's feeding the entire building. So we'll get takeoffs going left and right. The returns are coming back, and here's my common pipe. So I'm either flowing in this direction, or if I am injecting some boiler flow, an equal amount is coming back from the system. So in fact, it was, even though it looks different. And in fact, today there's basically 4 standard configurations. Some of them lend themselves more friendly to certain applications. We'll talk about it later, but this is a very common, and this is very common in the chiller world, where this is probably going to be pretty more common that you'll see in the heating world. So a real quick thing, always look for it. Always look for the common pipe. So in this example here, We have 3 zones. We have 3 secondary circuits, and we have 3 common pipes, common to both the primary and common to the secondary circuits. That is a properly piped and designed system. Quick picture, old boiler room at FIA has since been upgraded, but we wanted to highlight it here. We're doing some full reset because at the time we had cast iron non-condensing boilers that had temperature limitations. So I'm showing a quick example of an injection pump, a variable speed injection pump that is injecting into a constantly circulating heating loop, heating the terminal units in the building. And here is the common pipe and the common pipe. Technically, you could almost call this primary, secondary, tertiary. Small example, small application, but that's a clean, accurate installation. Again, I mentioned chillers, very common. And here's that arrangement where they want all of that warm water coming back from the fan coils. They want to really load those chiller barrels with the warmest water possible. So they encourage that type of common pipe connection. So the reason you want it, he actually has an article that I was able to find in a technical manual back in the 70s, I think it was written. That's how long ago. And there, someone would say, hey, I got a primary secondary system because I have a primary pump back here, and I have a secondary pump here, and I have a common pipe, is what they're claiming. And what he goes to explain is that with this valve repositioning, you basically put the primary pump in series, and the motor overload as frequently will occur, meaning when that valve closes to bypass, you have that primary pump's pressure differential in series with the smaller secondary. That's a no-no. You wouldn't do that. That is not primary secondary. This is truly primary secondary because here we actually have a common pipe. So I'm not overemphasizing it, but every primary secondary system needs to have one. Got called out to a building in Brookline, right outside of Boston in Fenway Park. And it was 10 large apartment buildings that were converted to 10 very expensive large condominium complex. And each building received its own energy management system with its own 3-way valve and actuator and reset control and its own distribution pump. And back at the boiler plant, they had a huge, I think it was Cleaver Brooks, and a large 60 horsepower distribution pump that was responsible for pumping heat through the 10 buildings. Upon commission, as the heating season arrived and these things started to work, suddenly they were snapping at the linkages. And the linkage is a little arm that connects the actuator right here and the 3-way valve that has a flapper inside that repositions based on outdoor reset. And these linkages were snapping. And so we finally got the call to come out and look at it. And it took a while because it's not nearly as clean as this drawing here, but eventually that's what we drew. And we realized this is exactly what he said back here. This is not primary secondary. There's no common pipe in this example. This distribution pump is in series with this valve and eventually this pump potentially. But this is why the actuators, the linkages were snapping. This pump's pressure differentials was so high, the valve couldn't react against it. So the people would say, well, what should it look like? And this is just a quick example, but what we're doing here is we're just showing sometimes in the primary secondary world, this would be referred to as a crossover bridge. And within that crossover bridge, here's my common pipe. It's common to the primary, and it's common to my secondary circuit. Go that way, I can go that way, I can go up the bypass. But that's a common pipe, and that would solve that pressure differential. This valve would never even see it because this common pipe would handle it and take care of it. So another detail is the flow rate characteristics within that common pipe that can occur. And in most multiple boiler systems that are installed today occur all the time. So here's a quick example where they say the primary flow rate is greater than the secondary. So 150 gallons a minute, I have a secondary circuit with a pump that's sized for 100 GPM. So you say, well, how's that going to work? Well, when the primary pump is running 150 gallons a minute across these T's, All of a sudden, this pump comes on, 100 gallons a minute, goes across this set of T, this T, enters into the suction of the pump, travels through the secondary circuit, comes back down. What didn't go up through the secondary circuit flows across the common pipe, 50 GPM, and it meets the 100 coming back, so the primary is back to 150 gallons a minute. And this all works because of this decoupling, this hydraulic isolation of that common pipe. So I can have different flows within that common. You could have an example where the primary is equal to the secondary. In this case here, if the primary was only providing 100 and the secondary only wanted 100, when the secondary pump came on, there would be no flow in the common. 100 would come back down that other T and back onto the primary, but there'd be no flow. There'd just be water sitting there. And if this secondary pump was to shut off, you'd immediately have 100 gallons a minute moving across the common back into the primary. The final example is when the primary flow is less than the secondary. And in that example, you say, okay, the secondary pump's looking for 100. How are you going to do that if you're only providing 50? Well, what would happen is 50 would enter one side of the T. I would have 100 gallons a minute from that secondary pump. As that return is coming back down and it hits the return T, it splits. 50 moves backwards, joins this 50 to provide 100, and then the remaining 50 jump back onto the return, the primary main return, and head back to the boiler plant. In this, right here, this example is what he did back in New York in 1953. This is what he could see in his mind, that if I decouple it, if I eliminate the pressure drop, I can have different mixings of flow rates. And that's how we took that 220 with 20 gallons a minute and made it 40 gallons a minute of 200-degree water. He'd run around and say an example, whatever enters a T must leave a T. You know, something very simple, but that describes the flow rate characteristics within the common pipe. And one last thing, and this kind of gets into the weeds a little bit, but it's the mathematical proof of what he described. So if you just kind of follow along with me, we'll work through it together. But what we're saying here is I have a secondary circuit that has a load of 200,000 BTUs, and it's designed at a mean water temperature or an average water temperature of 140 degrees. So at a 20-degree delta T, 200 MVH over here equals 20 GPM. So that's the size of this secondary circuit pump, 20 GPM. And he wants to provide a 200,000 BTUs at an average water temperature of 140. Well, when you say the mean water, you split it in half, 20, so take 140, add 10 to it, there's my supply of 150. The other part of that 20 degree minus 10 from 140 is my 130. So I need to have a supply temperature of 150 at a flow rate of 20 gallons a minute that will take a 20-degree drop, and that will transfer 200,000 BTUs through these terminal units here. The question becomes, what do I have available? Well, from the boiler plant, it looks like we have 210-degree water available. So what we're trying to figure out is, okay, what's the flow rate off of that distribution? What do I need to come across this crossover? And what's going to happen here in this common pipe? Crossover bridge return water temperature will equal the secondary return. What are they saying? If I know I'm coming back at 130, I know that 130 has to be the return temperature over here. Because how am I going to take 210 and make it 150? I'm going to have to take some of that return water. So some of it I will, and this is part of the heat balance equation, to mix down to 150, and the residual that I didn't use is what's returning back to the primary return. So what I'm saying, when they make that statement, what they're saying is, look, we know we have a return temperature of 130 and a supply of 210. So across the crossover bridge, the delta T is 80 degrees. That's a big delta T, but it works. And you can take the system sizer and you can use scale 1, or you can just show the math formula. But if I'm trying to move 200,000 BTUs at an 80-degree delta T, I'm going to need 5 gallons a minute. And so I plug in that number right here. So I'm going to be using these balancing valves. and I'm going to provide 210-degree water of 5 gallons a minute. So if I'm pumping 20 GPM of 150, it's coming back 20 at 130. I know I'm stealing 5 GPM of 150 here, excuse me, of 130 to blend with the 5 of 210. So that means 15 gallons a minute 15 gallons a minute is moving backwards. The residual 5 is returning back onto the primary. So this 5 here has to match this 5 here on the crossover. And the difference moves backwards. So he'll just say mathematically, 15 GPM, where do we get that? That's right here in this common pipe of 130 plus 5 of the 210, which is coming off the primary, equals 20 times 150. Just doing the math, 1950 plus 1050 equals 3,000. 3,000 divided by 20 GPM is a temperature of 150. That's a heat balance equation. So let's jump into some examples real quick before we run out of time here. Again, here's a quick example, very common, multiple chiller system. You see this a lot in perhaps a college campus distribution, feeding classrooms, offices, dormitories, certainly in hospitals, college institutions, etc. Again, fortunate enough, he actually talked about this that far back, showing primary, secondary. Here's my common pipe. I have a distribution, and here are my 3 chiller barrels. So he was referencing that primary, secondary had a place with large chilled water applications. So they're just showing, you know, a quick example here of flow rate for the secondary load is 1,500 gallons a minute. One chiller plant is on, and he's flowing the same. There's no flow. There's no flow in the common pipe at this point. Again, just highlighting this primary, secondary orientation, and most importantly, this common pipe. Here it is over here on configuration A. Chilled water coming back, common pipe, chilled water being produced by the chiller plant out to your distribution. This has become very popular over the last 10 years or so as the industry has embraced ModCon high efficiency boilers. A lot of the boiler manufacturers are actually saying, look, if you're going to put my boiler in, I want you to connect it to the existing or new system with primary, secondary tees. We're actually going to provide our own secondary pump. And the reason for this, why we can't just plug that boiler most times into an existing system, had to do with the type of heat exchangers that were first being used when these ModCon boilers were being manufactured, was this water tube. And characteristically, it just came with an inherently high pressure drop. Very, very different than the old sectional cast iron boilers that had virtually no pressure drop. So the manufacturers were concerned that they wanted to provide adequate flow through these tubes. So they said, look, at the way we can ensure that to happen is we will provide our own pump and have our own tees close together so that this pump supports and takes care of the flow and pressure drop needs here. But because of the closely spaced tees, it does not inject any flow up into here unnecessarily. And conversely, the system pump is hydraulically isolated from the boiler plant. Here's just a kind of a quick snapshot of some of those heat exchangers and what their corresponding flow rates were needed based on the BTUs of those models, of those boilers, and what the corresponding pressure drop could potentially be. These are much higher than what we were used to. So the way to handle it, and the way we have, is to use secondary pumps on the boiler plant, piped in primary, secondary. And here's just another quick example. Multiple boiler plants, very, very popular application, connecting them to the distribution main through a set of closely spaced tees. Each boiler having its own boiler pump to support the flow and pressure drop of each boiler's heat exchanger. That's very common. One quick comment on multiple boilers. Why not use one big boiler? Why use 3 or 4 smaller boilers? And it kind of can be answered right here in this, it's almost like a bin data chart. It's based on weather. And this is how they can develop these profiles. And what we're showing here is when the day comes and you're at design conditions, you need all of that BTUs, all of that horsepower, so you better have it. But the majority of the heating season, you have one big boiler that can support it. You're way oversized for the majority of your heating season. So your plant's going to run very inefficient and short cycle quite a bit, versus multiple smaller boilers with 2 or 3 boilers off and one boiler being tasked to support the building. That one boiler can operate usually pretty efficiently, and the other 3 are off, which the building owner appreciates as very efficient because they're not consuming any fuel. So that's a really popular reason why multiple boilers make sense. It just allows the system to run more efficiently. Couple of sentences: bullets more efficient than a large boiler, substantial capacity, even if one boiler does go down for service. And maybe from a physicality, just installation or renovation of an existing plant. Smaller units might be easier to install, easier to work on down the road. One quick comment on piping. With multiple boilers becomes multiple piping possibilities. And really, these all exist out in the field over the years, but this is really the ideal. This primary, secondary, like we just talked about, has a lot of benefits, inherent benefits, efficiency-wise. A statement made by one of the heating engineers in the industry that does a lot of writing, and he was referencing multiple boiler plant. Another critical requirement of maintaining this high efficiency is preventing heated system water from flowing through non-operational boilers. We don't want that. And that's exactly what you have with a system like this, where this is a multiple boiler. They're not claiming primary, secondary. They're just saying a multiple boiler, but they actually have heated system water flowing through all 3 boilers, whether they're firing or not. Another quick example I'm just going to fly through has to do with this is a 1-pipe primary, secondary, but it's really not recommended. You'll see it out in the field, but it has some built-in potential difficulties. So I'm just going to run through a quick example here. I'm going to say I have a 300,000 BTU boiler that's getting replaced with 3 smaller 100,000 BTU boilers. So I know my primary main pump, my distribution pump, is pumping 30 gallons a minute, and I'm going to say it was designed at 190 degrees on a design day with a return temperature of 170 gallons a minute. So theoretically, I have a staging control. I'm controlling these 3 boilers, and I'm under design load. And this is what's going to happen. This is how this works. The first boiler comes in because the supply sensor says, hey, I need to be at 190. So the first boiler comes on. He's sized at 100,000 BTUs. Theoretically, if it's done right, sized right, the pump is pumping 10 gallons a minute to transfer 100,000 BTUs across a 20-degree delta T. What's the inlet temperature to that first boiler? When the system is up and running and I have design conditions, my return temperature is 170. I'm going to have an inlet temperature at a flow rate of 170, 10 GPM, because it's a 100,000 BTU boiler. I'm going to have, if the boiler's transferring his 100,000 BTUs, I'm going to have a temperature of 190 degrees. To which you'd quickly say, wow, that's great. That's exactly what I need over here on the supply, 190. The problem is 30 gallons a minute are right here. Only 10 move this way. This is another example of that common pipe and flow rate characteristics. If I only take 10 gallons a minute off of that main, what do I have left over across the common? Well, the answer is going to be 20. At what temperature? 170. I'm going to do some mixing here at this T. I'm going to knock it down. It's going to become 177. Staging control is not going to be happy. He's going to say, hey, I need more help here. Second boiler comes on. What's the second boiler's inlet temperature? Right off the bat, I got 177 on the main. It's going to be 177. So right off the bat, I have 2 different inlet temperatures to these 2 boilers. Boiler transfers his necessary 100,000 BTUs. I'm up to 197. I got that blending going on again. So I'm only up to 184 on that main. I need that third boiler to come on. Inlet temperature here, 184. Outlet temperature, what's the required? What does it need to be at? It's got to be all the way up to 204 to blend with that 184 of 20 gallons a minute to get me that 30 at 190. That's why this, a lot of times the aquastats in these boilers aren't even set that high. So inherently not as effective. better example would be these closely spaced tees where each boiler sees the same inlet. That's a much better example. Another method that can be used, and it's become popular, is a low loss header or a primary secondary header that acts like a primary secondary set of tees. We see them out in the field all the time. And just kind of a cross section, how does it do what it does? Based on the pipe diameters that it's connected to the boiler plant and the system side, they engineer the diameter here so that the velocity inside here is less than 1/2 foot per second. It creates a quiet zone. It's a decoupler, just like a set of closely spaced tees. The other thing that they decided to take advantage of was at that low velocity, as I'm releasing air from my heated water from my boiler plant, I'll just add a high capacity vent and now I have my air separation. So now I have no air making it out into the distribution pumps. So it's a very popular, can be very effective. Sometimes guys will take out a third step and they might even use it as a dirt particle separator, and they'll attach a blowdown valve to blow down any sediment that might be coming back from an older dirty system. So again, it works just like a set of primary secondary tees. Like we talked about before, if there was no flow in the, if the flow rates were equal, there'd be no flow in the common. If the flows were dissimilar and the system side had a greater flow rate than the boiler side, this is what would happen. You'd have some blending that might be okay. And you could have a third scenario where you might have more flow on the boiler plant than you do on the distribution side, which would be a bad thing in terms of taking hot boiler water and elevating my inlet temperature, which could affect, depending upon the boiler plant, if I'm dealing with modulating, condensing, high efficiency boilers, that's kind of a design no-no. But just showing another example. And lastly, one last thing to kind of address that scenario of the temperature entering the boiler plant is some of the manufacturers now have the capability of providing or sending a 0 to 10 signal to ECM boiler pumps. They have the technology to control the speed of the pump, which means they control the GPM of the pump, which means they might eliminate that scenario of over pumping the boiler plant. And this is a quick example where if I have flow rates going on here and I'm in the boiler plant at a certain flow rate, the boiler plant's pumping 150 GPM, the distribution pump's pumping 150 GPM, there'd be no flow in the common, everything is adequate. If something changed and all of a sudden I'm increasing my flow on the secondary, and so I have a little bit of over pumping, I bypass, what am I doing to the temperature coming out of the boiler plant? I'm blending it down. So I'm looking for 140, I only have 130. So what do I need to do as a boiler plant? I need to kick on that second boiler because the outdoor reset schedule says, hey, I need 140 at these set of conditions. So the second boiler plant comes on. Now I have 300 gallons a minute because they're fixed flows. I take the 200 to the secondary, which satisfies the energy management system. But look what I'm doing on the common pipe. I am now pumping, I'm over pumping on the boiler plant. So I'm taking that 140-degree water and I'm mixing it with 100-degree water. All of a sudden, I'm elevating my return. And as a quick chart from one of the modulating condensing boiler manufacturers' efficiency curves, as you start to take that return water and you start to elevate it, look what it does to the slope of those efficiencies at the various firing rates. So you want to do everything you can to try to avoid that. And here's a quick way of doing it. If you have a boiler with a fixed flow and you have a turn down ratio, here's a quick example of a 500,000 BTU input boiler with a 5-to-1, and I keep that fixed design flow rate, which I need when I'm at 100%, but when I'm modulating down, look what it does to the delta T across that heat exchanger. It gets very, very tight. It can lead to a lot of short cycling, which leads to a lot of cycles, which it can affect igniters and flame sensors and fan blowers assemblies. So a solution might be take that ECM technology, attach the signal from the boiler who's watching his inlet and outlet temperature sensors on the heat exchanger, change the flow rate to maintain the desired delta T across that boiler. And that leads to a much more efficient boiler plant and a considerable amount of less cycling of the boiler. And again, this is all being connected up here with our primary, secondary Ts. Here's just a quick example of one out in the field. With it's just 2 boilers having their own individual pumps. They have the 0 to 10s coming out of the boiler main control to influence the operation. And with that, I think what I'd like to do is open everybody up. Or if you have any questions, maybe I should start there. If you have any questions, fire away, or fire away. You could unmute yourself individually, I suppose. Or if, Rob, I don't know if you've encountered any chat questions that needed answers, or if they've already been answered.
George,
and we can, yes.
The one question came up, I think we answered it, but I think it was kind of questioning multiple boilers in primary, secondary with like a multiple Ts. And I think you're right about
that last example.
Yes, I think that was the question right there.
Meaning what? To do it, not do it, what happens?
Yeah, I think it was to do it in the sizing, and I think we've answered with always do them as one set of Ts with common boiler manifolds. Is that
like the second picture, the final example, yes.
Okay.
That is definitely the best way, because it takes away that situation where as you're starting to get closer to colder temperatures, so you're getting closer to design loads, and you're needing that elevated supply temperature, you're changing the inlet temperature to each boiler, as the boilers become online. Technically, the primary, secondary Ts are correct in terms of isolating, but it's that other factor of changing water temperature from boiler to boiler to boiler. That's the downside to it, because it forces the downstream boiler to provide even higher temperature because of that mixing that takes place in the common. So
I think that got it, George.
Okay, did that seem to be the consistent question?
Absolutely.
Okay.
I just have one question, George.
Yes, right.
Besides a great presentation, you guys are doing a great job. Your knowledge is great with this. That system size, are they going out? Yeah.
Yeah, I have this holding with me just in case I got that question, Ray. Yes. The woman, Erin, I finally got all the addresses from all the emails I received from everybody, and she's starting the process actually today, getting those in the mail to everybody that requested them, Ray.
Yeah, that's a great tool.
It is.
Along with the presentation, it's great. I mean, just to quickly go over whatever you needed, if the flow or the GPM,
right,
or the BTUs, that thing is phenomenal, I think.
Yeah, no, it's a very good tool. It's a funny thing, and it's been around a long time. What I just want to, what we're doing here, just finishing up the presentation. If you have to take off, I certainly understand. We've been going at it for about an hour. But just with regards to this presentation, and then some of the other stuff we've been talking about, to make sure that you guys are aware that you have access to a lot of technical stuff through FIA's website. And what Rob has us at the homepage right now, when we're clicking on one of the drop downs, it says Ask George. And within that Ask George, there's a couple different things. There's a section called George's article, and it's just a compilation of all the articles I've written over the last 20 years.
Wow.
For some of the trade magazines. And then we have this other segment called George's Basement, and I think they listed it that way because I spend most of my time in basements looking at problems. But that I referenced earlier, that collection of videos, we were able to get them loaded up on our website, and it takes you to YouTube, and there's about 9 videos. And if you have the desire, feel free to click away. It'll take you to YouTube. You'll have stuff on primary, secondary, and all kinds of subjects. Very technical, but very, very good. And it's the kind of lost treasure of the beginning of the hydronics industry that we all partake in today. Right below the Gil Carlson is all the manuals that Bell & Gosson has written for steam and hydronic, referred to as TEH manuals. We have a link right there. If you click on it, it's going to take you to all of the manuals. You can save them or download them or just read them online. but it's quite a collection of all the different stuff that B&G has contributed to over the industry, over the years in the industry. And it's free access. Just come to our website, get right to it. So just more technical information. The final two things at the bottom here is Bell & Gossett also participates in the steam market. We play with condensate pumps, boiler feeds, vacuum pumps, steam traps, vacuum breakers, radiator traps, steam vents. So we've already, and I have contributed to this, but there's a lot of steam articles that are archived. So if you had a question on steam, don't hesitate. And the final thing is Counterpoint. I used to put out a thing for B&G years ago called Counterpoint. And what would happen is one side, and it was intended for the wholesalers to locate them on the counters for the trade, for the contractors that would be coming in and picking up product. And on one side, it was an article about hydronics, and you'd flip it over. And the other side had an article on something about a steam system. So it's just a very short, brief, but good, information on two different subjects, hydronics and steam. So I'm taking enough of your time. I just want to share all of that with you. Know that it's at FIA's website. It's some pretty good stuff. Obviously, Rob's got a lot of our training classes, which obviously over the years you might have referenced when we used to do them in person. We're now doing them obviously virtual, and we're listing them as webinars. So we'll continue to do this. We don't know what the future holds, when this thing's going to change, but until it does, we'll certainly continue to load up our seminar list as well as do our email blast to make you guys aware, and ladies aware, of the various offerings that we're going to try to provide, during this kind of uncharted waters time that we're going through. But anyways, I guess without wasting any more time, I just want to say thank you. Thank you very much for your time and attention. And as always, be safe. Not sure if you're aware, we have a couple of seminars this afternoon. Rob's doing Lockaba Connexus at noontime. And then we have kind of moving away from piping technique, but getting into some product. Tecmar has some Wi-Fi thermostats and relay boxes that are kind of new to the industry that we're going to spend a little bit of time just sharing and reviewing with. So without any further ado, I'm going to shut down the meeting if no one else has any other questions.
George, excuse me.
Yes, Ray.
That Tecmar, is that the one you had last week?
It is. It's the same one. It's the same.
Okay,
So if you've
right,
seen it,
right.
yeah, you're not missing anything.
Right.
My feelings won't be hurt one way or the other.
No, I didn't know.
I
Like one and two coming up. That's why.
Say one more time, Ray.
I didn't know if there's a second.
Yes,
added to that.
yeah, Rob and I again together, and we're coming up with in different subject matters, maybe within the same product line, but different components, and focus on whether it be mixing controls or staging controls or something within the Tecmar world. Yes, we're definitely working on that.
All right.
Okay.
Thanks a lot.
Thank you. Thank you, everybody.
Be safe.
Yeah, exactly. Great. Thank you. Everyone be safe.
Thank you.